33 years ago, a serious meltdown accident occurred at 3 Mile Island. Retrieval of the molten fuel lasted 11 years. The dismantling will start 20 years from now. 26 years ago, the worst ever nuclear accident happened at Chernobyl. The sarcophagus is degrading. There is no clear roadmap towards decommissioning. On top of that, in the case of Fukushima Daiichi, unimaginable, unexpected difficulties have to be expected. This is an extremely long and thorny path. It will take many years with enormous difficulties. There is no precedent of simultaneous decommissioning of multiple reactors. Destroyed containment vessel must be repaired. Robots operational in high-level radiation must be developed. There is no past experience in the world. How can we decommission Fukushima successfully with all these challenges? Global experts will discuss with us. Project Wisdom. This is part 2. In part 1, the reasons why TEPCO accident went as bad as level 7 and the actions by authorities were discussed. We will now discuss the decommissioning of Fukushima and the disposal of high-level waste. Our members are with us from part 1. Thank you for staying with us in part 2. We welcome your tweets. Please use the hashtag for your tweets. We have a senior commentator, Mr. Mizuno. Mr. Mizuno, regarding Fukushima Daiichi, the government says it is now in a status of a cold shutdown as of December. The roadmap towards decommissioning has been announced. What is the procedure going forward? The government said it will take 40 years at maximum. There are 3 phases. Please look at this. First of all, within 3 years, this is phase 1, unit 1, 2, 3, 4. From the spent nuclear fuel pool, the fuels have to be retrieved. In order to retrieve, above the buildings, cranes have to be placed. Unit 4 will be done first. Debris is being taken off. Next is phase 2, which is expected to last until 2021. So that is until 2021. This is a preparation to take the molten fuel. What is preparation? High-level radiation is the risk. Heat is generated. Therefore, flooding is required. Radioactivity will be shielded. Cooling will be done by flooding, which means the broken parts have to be repaired first of all. Otherwise, the water will leak. That is right. Whether repair is possible, it is highly radioactive. Operators may not be able to access. Therefore, whether repair is possible, robotics development is a question. A fresh robot has to be developed. That is right. The flooding, if flooding is successful, then finally it is phase 3 up until 2051. The molten dropped fuel has to be retrieved. The entire system has to be dismantled. In order to retrieve, remote control robotics is required. For example, this containment vessel is 35 meters high. Therefore, you need a long equipment to reach the bottom. Thank you very much. Let us introduce the comments at the website. These are the comments at the website. What are the challenges that bars decommissioning? That was the question. Number 1, it will take time to develop a robot that can move around the destroyed reactor building, repair the building, and retrieving the radioactive material. Comment number 2. In order to find the place, there are too many uncertainties about the risk of the dispersal. Some comments from across the world.
Well, because the stations have been very badly damaged by these explosions, decommissioning is going to be very difficult. By decommissioning, I mean removing all the fuel from the reactors and taking it away. Reactors have all been very heavily damaged by these hydrogen explosions. And that means that they can't use the equipment that was there already in the power station designed to do it.
We have one severe accident with an off-site release like this at Chernobyl. That was 25 years ago, and we are still dealing with the legacy of the accident. There is no effective plan to decommission the reactor. The biggest challenge that Japan faces in this regard is to remove all of the fuel and the melted material inside the core of the reactor. This is extremely radioactive. It's going to have to be treated and handled with great care using robots and technology which still has to be developed.
The first obvious challenge is the long time duration of this activity, 40 years. There is a destruction, there are active elements, there are leaks. It will take certainly longer and it will be more expensive. In practical terms, to have 2 generations of people of continuous effort, or to have a father and their son working all their life.
We pass on to the future generation, to our children. It takes so many years. Now from the U.S., Mr. Jack Devine, at 3 Mile, you were the recovery engineering manager. You were on the site. You were actually on the site. Based on that experience at Fukushima, how can the Fukushima be decommissioned?
Thank you. Well, my first thought is that we ought to look at this not as a decommissioning job, but as a hazard removal job or as a threat removal job. We've got 4 damaged reactors, 3 melted cores. Several of the comments a minute ago referred to the difficulty of removing the fuel, and I certainly agree with that. But the objective is first and foremost to remove the threat, the ongoing hazard that site presents to people on the site and to people off-site. And as part of that, for the off-site community to get people back in their homes as quickly as possible. This may well take 40 years to decommission all 4 plants, but I would propose that in the near-term time frame, very high focus should be on those parts of the damaged plants which do represent a threat. At TMI, our focus was picking up the fuel, eliminating potential for criticality, getting rid of water and leak potential, getting rid of any chemical combustion potential, all those kinds of things, as opposed to dealing with the many other tasks that ultimately have to be conducted to decommission.
Thank you very much. We will look at the 2 past accidents, including 3 Mile Island and Chernobyl. How are they being decommissioned? Video. 33 years ago, a serious meltdown occurred at 3 Mile Island, United States. A large amount of nuclear fuel melted. Inside the reactor, they solidified like volcanic lava. A major difficulty was cutting the solidified fuel into pieces to retrieve. Retrieval of fuel must be done underwater to shield strong radiation. Underwater camera was required to observe the inside of the reactors. Specialized remote robotics had to be developed. Retrieval started 6 years after the incident. Operation lasted 11 years. In the case of Fukushima Daiichi, reactors and containment vessels are damaged. They must be repaired in order to fill the reactors with water. The retrieval at Fukushima will take much longer than 3 Mile Island and will be more difficult. In the former Soviet Union, Chernobyl accident was the same level 7 as Fukushima Daiichi. Chernobyl decommissioning is not progressing smoothly. The reactor was completely destroyed by explosion. Lead and concrete were used to cover the building. Sarcophagus, stone coffin, was made to prevent the release of radioactive material. However, that sarcophagus is deteriorating. There is a risk of collapse. Repair works are still ongoing. In order to decommission, about 100 billion yen, a massive amount of money, is required to cover the entire building. Operations can start only after building the gigantic cover. 25 years after the accident, and a clear roadmap towards decommissioning is not yet visible. A 3 Mile Island. Mr. Devine, you were on the site regarding retrieval of the molten fuel at 3 Mile Island. It was highly radioactive. Robot had to be developed for the purpose. What is the kind of robotics that was used?
Well, actually, we did not use robots in the sense that most people think of them. Originally, our planning was to develop robots to remove the fuel with no human beings there. We didn't proceed in that direction for 2 reasons. One, we were uncertain about the condition and the location of the damaged fuel, and for that reason, we felt that it would be very difficult to design a robotic system that could handle any possibility. And secondly, we were able to achieve a condition in the building such that we could locally reduce radioactive conditions, radioactivity, radiation fields, and contamination so that people could work. So we developed a set of very flexible remote manual tools with operators handling them through water, and we built a large mock-up, a full-size mock-up, just outside the reactor building so that every one of those tools could be tested. And then as we proceeded, that system gave us a great deal of flexibility. Now, will that be possible in Fukushima? We don't know yet. But my counsel so far has been that we ought to work very hard to make sure that we develop tools that have a great deal of flexibility and simplicity as much as possible, rather than rely on very complex robots with no human beings there. And it is possible. We did that at TMI, and at the beginning, a lot of people thought we would never be able to defuel the reactor that way. We did the whole thing successfully.
Mr. Devine, it solidified like a volcanic lava. It was very hard to cut. You had to cut into pieces in order to retrieve. What were the tools that were used? Who developed and how?
We used a large drill system that was essentially the same thing you would use for a mining operation. We received a great deal of help in that project from the U.S. Department of Energy, who was an excellent partner in helping us develop the tools. And we used that tool both to retrieve samples and then later on to break up the portion of the core that was a very hard crust into small pieces, and then to use the flexible tubes that I described before to put those pieces into canisters. You know, I have to emphasize that it might seem to be a crude and simple approach, but that approach turned out to be the one that fit that work the best. The system for breaking up the hard material, however, was a very high capacity mining type drill.
Another question. Close to the premises, the radiation level was high. What about the exposure of the operators? In order to reduce exposure, the operation had to be very efficient. What about the training of using new tools by the operators? How did you train them?
As I just mentioned, those are two excellent questions. First of all, with respect to the radiological conditions, we created an envelope within the containment building where the radiological conditions were habitable. And in fact, we had crews working for a normal work week in there for a number of years defueling. Initially, we didn't think we'd be able to get it that clean and the radiation levels low enough, but we did. Provided local shielding, put a collar of water above the reactor building, used the walls of the refueling canal as shield walls and then added shielding to them, built a shielded platform over and you saw a video a minute ago of that. And that was a big step. As far as training, very importantly, as I said, we built a full-scale mock-up. We used the turbine building, which had been undamaged, to get a dimensionally identical setup. So every tool that we wanted operators to use in that building, they had a chance to practice with in a clean environment. We would have them practice with their full anti-contamination clothing and respirators, so they would be using it with the same level of difficulty, but with no radiation at all. And when they became proficient in the mock-up, then they would go into the reactor building and remove that next part of the fuel.
Thank you. Dr. Klein, the NRC, what was the involvement in the 3 Mile Island?
Well, as one would expect, the regulator is definitely active and involved in that process. I think that's one of the areas that Japan needs to look at, and that is to really seriously look at their regulatory structure in Japan. And I believe they would be very much at an advantage to make it a totally independent agency. Again, the government of Japan needs to look at what works in their country, but I can tell you from the United States, having an independent regulator, highly technically competent, that can do independent analysis and assist the industry is, I think, a way to go. But clearly, as the regulator looks at what the industry will do, worker protection and safety is number one. I think Jack Devine articulated it very well as the first important thing to do is to make sure that you do the work safely, you protect the workers. Sometimes there's an advantage to wait to let the radiation levels decay naturally so that when you go into areas, you don't unnecessarily expose workers to undue risk. I think Jack also indicated what's important is, I think, to let people move back into the area safely. So I think the first issue I would recommend is make sure that the reactors are in a safe cold shutdown monitoring mode. Develop your plans logically protecting workers, but at the same time, look at the areas where people were evacuated and see if you cannot let people return to their sites in a safe manner.
Thank you. Mr. Barry, who used to be at CEUR, in order to retrieve fuel at Fukushima, regarding the reactors and the containment vessels, it must be flooded with water. However, the vessels are damaged. How can we flood at Fukushima? How can we fill the water?
I have very little to add to what has been said by Mr. Devine and Dr. Klein. I agree entirely that a very pragmatic approach will have to be taken, and that relying entirely on robotics would probably not work. Now, of course, plugging the leaks in the pressure vessel and in the primary containment is important, and then of course, it might be the first application of robotics.
Thank you very much. Mr. Barry is the advisor to AREVA. AREVA reprocesses the fuel. Is reprocessing of the molten fuel possible, Mr. Barre?
Well, first, the question will be, what about the undamaged spent fuel? As you know, there is a huge inventory of spent fuel presently on the site, both in the units spent fuel and also in a pool which is common to all the units. And this can easily be reprocessed. Now, when you come to the debris, probably reprocessing will not be the answer, but conditioning will call for a lot of technology, but not reprocessing the debris.
Thank you, Mr. Mizuno. The molten fuel, the retrieval needs a lot of development, training of the crew. It is going to be extremely difficult. It will take many years. But after the retrieval, the disposal is still a remaining challenge. At the moment, at Fukushima, considering the characteristics, what could be done for Fukushima? In Japan, regarding the spent fuel, it was to be reprocessed. That was the plan, that it could be reused. Plutonium was to be extracted, high-level waste would be separated. That was the plan in Rokkasho of Aomori. A plant was made. It is under trial. However, for a molten, destroyed fuel, this was never planned. The destroyed, damaged fuel, different metals are mixed up together. Therefore, an integral fuel is different. The composition is entirely different from ordinary fuel. At Rokkasho, the reprocessing plant probably cannot be used. Experts say Rokkasho cannot be used for damaged fuel. On top of that, in order to cool the reactors immediately after the accident, seawater was used, which means salt is mixed in the damaged fuel. When salt is present, reprocessing at an ordinary reprocessing facility will not be possible. The reprocessing system will be damaged because of salt, and therefore ordinary reprocessing system cannot be used. Then what can be done? Answer is not found yet. However, what has been retrieved, first of all, must be stored in an interim manner. However, where can it be stored? Again, siting is terribly difficult. Should it be somewhere away from Fukushima? That sounds extremely unlikely and difficult. On the premises of Fukushima, whether storage is possible to keep the damaged fuel, for the time being it has to be stored. Then the future disposal has to be researched and developed. Mr. Jack Devine, at 3 Mile, the retrieved fuel had to be disposed. Regarding Fukushima damaged fuel, what can be done for the disposal?
Well, I'll tell you what we did at 3 Mile Island, and again, I'm going to go back to what I said before about the idea of looking at this project as being fundamentally one to eliminate risk. So it's important to get that fuel from where it is to a safe place. That safe place does not have to be the place where it's ultimately disposed. And that's the approach we took at TMI. We designed canisters, very, very rugged steel canisters, in a configuration that would preclude criticality, that is a nuclear event inside the canister, and that would also recombine hydrogen, if there were any hydrogen generated from that fuel. We put the fuel fragments into those canisters. We stored them underwater. We built casks and transported them to a facility in Idaho, a Department of Energy facility, where they can be observed. As you may know, we have not yet decided as a nation what we're going to do with our high-level waste. But we put that fuel in a condition where it is unquestionably safe for as long as people want to keep watching it and decide what to do with it, rather than have the decommissioning project or the recovery project be victim to trying to put the fuel in its ultimate condition right at the start.
Dr. Schurers, how can the fuel be disposed of?
Well, I think that is one of the challenges that we really don't have an answer to internationally. We do have low and medium level radioactive waste sites, but we don't have any high level radioactive waste sites. And